Hi guys, week number 4, and I hope you had an awesome weekend. Today, per usual, I'm gonna give you some feedback about what you already submitted, and I'm going to remind you what we have for next week and go over 3 chapters, chapters 10 and 11 from our biomechanics book, and then the first chapter of our motor behavior book today. So we're going to finish up the first textbook and we're going to move to the second textbook today. Okay. Before I forget, I moved the office hours from tomorrow to Wednesday because tomorrow I have to talk to our student athletes. There is a seminar I'm leading, so I had to do it. However, if anybody needs to talk to me and it's urgent, let me know. I'll be checking my emails and we will schedule something special just for you. Okay? No synchronous meeting this week, but we will have one next week. Right? So I'm going to go ahead and share my screen. And let me see. What I need to do here is this. Yes. So let me see. Cancel this. Share. Okay. This is our Moodle site, and this is what you had for today or for last night. I'm very happy. I'm very happy. I'm very excited. You're doing very well. So LO6, very high average of 96%, LO7, 91%, LO8, 88%, and LO9, we went back to the 90s, 91%. The only item that I have here in my notes that I need to address that most of you didn't answer correctly, there was a question for chapter 7. Which of the following observations is not associated with changes to the spine due to the aging process? And one of the choices was decreased lateral bending. Actually, you know, the strength, yes, goes down, flexibility goes down. There is loss of height, right? Hope you remember that the discs, because of the discs. And then actually there is we have observed increased lateral bending of the trunk, increased. So it was not decreased lateral bending, it was the wrong answer if that's what you picked. Okay, and that's the only thing I have here that I should address just specifically. Other than that, you did awesome, very, very happy. Looks like you're getting it, and it makes me, you're studying more, or you know, you understand what the LOs are asking, the items, the quizzes. So I'm happy. I'm very happy for you. Now for next week, 3 chapters, as I already said, the last 2 chapters of our biomechanics book, so LO 10 and LO 11, and then I will start over with chapter 1, which is from our motor behavior book, and that will be LO 12. All right, no synchronous meeting this week, but we do have a synchronous meeting next week. Cool. Yeah. All right, I'm gonna stop sharing this and I'm gonna start sharing our PowerPoints. So let me see. Chapter 10, there it is. Linear kinematics. All right, a lot of information again. I'll do my best to not send you a long video, however, to share enough information. At some point, the AC will start on, so there's going to be some noise. It's just the AC trying to keep me warm. Excuse me. All right, so linear kinetics and linear kinetics today and angular kinetics, the last 2. So we talked about kinematics, which was how we move, right? We talked about that. And kinetics is why we move the way we move. So the causes of motion. So this chapter is translatory. It's about translatory motion. so linear kinetics. And the next chapter will be about rotational, angular. So the most important concept in this one, and it has to do with physics, of course, is force. Okay, and force is not a term that we can easily define. We can operationally define it by telling what it does or what but we cannot really define its characteristics. So you see, it's a vector, right? We talked about vector, which is a magnitude and a direction, right? I hope you remember that. And forces may be push, pull, rub, which is friction, and blow, which is the impact. So force causes or tends to cause motion, changes in velocity, acceleration, or it changes in the shape of the object. Okay? Four are the characteristics of force: magnitude, direction, point of application, line of application. Magnitude, direction, point of application, and line of application. So here we see force, and we see force, internal force and external force, and we can see all four characteristics in both cases. Okay. We've talked about the Newton's laws in other courses, and I am sure you have talked about those with other instructors, not just me. Okay, there's the AC. Okay, so this is the first Newton's first law, which is called law of inertia. Okay, so unless it is compelled to change that state by external forces impressed upon it, every body continues in its state of rest, right, or constant velocity. This is the law of acceleration. So force equals mass times acceleration. Momentum, I just want to talk about this for a second. Momentum, P, equals mass times velocity. We talked about momentum a lot even in everyday life, right? So the higher the mass, the more the momentum, the higher the velocity, the more the momentum. Okay? Action and reaction, for every action, there's always an opposite and equal direction reaction. It's a vertical ground force. So an example of that is when we are stepping, running, jogging, walking on the floor, on the ground, there is a ground force reaction, which is opposite to the force that we are applying to the ground, right? So this is an example of how the vertical force fluctuates based on time. That was about walking. So another thing I want to mention briefly is that we have non-contact forces. There's no direct contact between two objects, for example. Perfect example, gravity. And we have a ton of contact forces, including GRF that I just talked about. We're going to talk about friction, fluid resistance in a little bit, elastic force, and so on and so forth. Okay? Yeah, this is what GRF is. I just talked about it, and this is how we measure it. This is a force plate or force platform, right? We push against it, and then we measure the ground reaction force, and by measuring the ground reaction force, we measure indirectly the force we are applying to the ground. So we can do that separately by segment. Okay, it would look like this. That's what biomechanists do. Friction. Let's talk about friction for a second. The force acting parallel between two contact surfaces that tend to rub or slide past each other. There can be friction without movement. There's friction right now between the clicker and my hand. Okay? The coefficient of friction has to do with the two surfaces. Okay? Because the molecular bonds are being created between the two surfaces, and The higher the coefficient of friction, the higher the friction we have, right? The friction force. So when you have something on a surface, let's say the clicker on my hand, right? When you have the clicker on my hand and I'll start pushing it, in the beginning, as I'm pushing it, nothing happens. After a point, it will start moving. So in the very beginning, as I apply force, I have what I call static friction. There's no movement. When there is movement, I still have friction. That's called dynamic friction. However, you see dynamic friction is a little lower than that part of the static friction, the highest, which is called instant of motion. It's where I apply that quantity of force that the clicker started moving. It drops. Why does it drop? Because those molecular bonds that are being created between the two surfaces, they're still being created, but they're made and broken. And then you see sometimes when something starts moving, then it feels easier to keep moving it, right? And the friction is constant, same. That's what's happening. Think about what's the word I'm looking for? When you're pushing, oh man, what is it called? Oh, it'll come to me. Just I'm a little bit too man. Anyway, I don't have the clarity, I guess, to find that word, but I'll come back to me in a little bit. So when something we're pushing, is not moving, at some point we'll start moving, and then it feels easier. I still have frictions called dynamic. Before I had static. After that instant of motion, I have the dynamic. Before that, I have the static, and there is still friction because the molecular bonds are still being created, made, but also they're being broken. Okay. All right, fluid. Fluid is liquid and gas. One. So don't forget that. The two basic things about fluid is density and viscosity. Density is the mass per unit volume, and viscosity is a measure of the fluid's resistance to flow. When there is fluid resistance, right, we have something that's called fluid lift force. And they're always, as you can see, directed perpendicular to the oncoming flow, but lift forces are not necessarily directed upward. Okay, remember about the airflow on a racing car that's trying to keep the car actually on the ground, right? So here what's going on is we have a drag, okay? So we have the drag component and we have the lift component. The drag component is always, as we said, opposite to the direction of motion. And you see the vector in between, which is a result of the lift component and the drag component, with the fluid resistance vector. Okay. Drag force. The more the coefficient, the more the drag force. And the more the frontal area, the more the resistance, right? Imagine a car that it looks like a Lamborghini, and then imagine a truck. The truck will have more fluid resistance, right? Because of the front area. The fluid viscosity, the more fluid viscosity, the more resistance, and the more velocity, the more resistance. That's what this tells us. All right, so when something is moving, right, we just talked about it. If the velocity is low, we have something called laminar flow, and there's no turbulence happening behind. So as you can see, the arrows are going against the direction of that ball, right? And if it's going fast, there's turbulence happening at the back. Okay. Now, we are trying to decrease that by using aerodynamics and hydrodynamics. And you've seen those suits, right? They even allow them in the Olympics now. All right. Magnus force. That's kind of exciting. I want to share this in case you don't know. Have you ever played baseball, softball, soccer? Right? tennis. So here what we have is we have a curved ball. So we have a curved path of a ball, and you can see that it rotates in a way that pretty much what's happening. What we have here is one side of the ball rotates against the direction of the air, and the other one the same direction. When it's against, we have more pressure. When it's the same, the bottom part, we have lower pressure. So we'll have high pressure, low pressure. And because of that pressure difference, that's the Magnus force. That's how we explain it, the Magnus effect. So the pressure difference makes the ball follow that curved path. Okay? So that's how it is happening. High pressure, low pressure. And it's obvious also over here. You see the dashed line, that would be if it was like a straight kick. But when we curve the ball, you see now that's a way different direction. Again, why? Because of the difference in pressure on the sides of the ball. High pressure, low pressure is going to move towards the low pressure side. Cool. Inertia, the force exerted due to the movement of the body. Okay. Elastic force. So here we have a kappa, which is a constant of like its stiffness, pretty much. Right? So the more stiffness, the more elastic force, and the more change in length, the more elastic force. So if this is stiffer and I bent it, the more stiff it is, the more elastic force it can save, and the more I bent it, the more elastic force it saves. Okay? It's like springboard diving. These are the free body diagrams that biomechanists use to analyze linear kinetics, static analysis. When I have no movement, right, the acceleration of the system is 0. This is an example. So if you add on each side, we have 500 newtons. Static analysis, no acceleration of the system. But when I do have, then we go to dynamic analysis, so we have acceleration. And this is just how it would look like with all the forces and all the rotations. Mechanical impulse. Work. Work I want to talk about. All right. So work equals F times cosine of an angle theta times S, which is the displacement. I don't want to talk about cosines right now, per se. I want to go here and explain something. So we'll have a box, like we'll have a table. You want to push that table from one side to the other side of the room. Sorry. Right. What's going to be the angle of the force, the line of the force? We have two examples. We have A and B. Where do you think you're going to produce more work? In scenario A or in scenario B? In scenario A, the angle is 0. In scenario B, the angle is 30 degrees. The cosine of 30 is 0.85, if I remember very well. The cosine of 0 is 1. So if you go back here, if you put 1 right here, you're going to get the maximum number, because that's the maximum cosine you can have, 1. Right? Anything below 1 will give you less work, which means that now, of course, if you push, you're going to push this way, because that's the way you're going to get most work with the same amount of force. Same amount of force, same amount of displacement. I have to push this way. This is the line, not this way. Make sense? Power, okay, energy. Okay, so energy here, power, we talked about power and how it is. It depends on time, right? Okay, so energy. Energy is going to be broken down into kinetic energy and also potential energy. That has to do with gravity. Now, if I throw an object up to the sky, like a ball, tennis ball, right? the energy, if the system is closed, remain the same. However, the kinetic energy can go up, fluctuate, and so is the gravitational potential energy. So if we go here, when I throw the ball up, the kinetic energy is maximum. Why? Because velocity is maximum when I release it. Velocity starts decreasing, and then it goes all the way up where it's zero. When you can see here, right, that if velocity goes up, kinetic energy goes up. If velocity is zero, then this will be zero. So here it makes sense why up here is zero and down here is the maximum. And as you're going up, is decreasing, right? Here, as in going down now, we have started having more and more velocity, so kinetic energy is increasing all the way here where we get the maximum. PE now has to do, as you can see, is the potential energy. It has to do with the mass times the gravity and height. Here, for example, we have zero height. The more height, the more P. At the apex, all the way up here, the highest point, of course, we have the highest is maximum. So I will have maximum P. As I'm going down, P is going to decrease all the way to hitting the ground, where height is going to be zero. And if this is zero, this will become zero because it's a product. I hope that makes sense. Pressure is force over the area that I apply it. So if I apply the same force on top of this, the area is really small, right? So I'm going to get a lot of pressure. It may hurt my thumb. If I make it the other way, so I have now more, the same force is going to be applied in a larger area. Does that make sense? So the same force on a larger area is going to give me less pressure, more pressure. Same force, smaller area. I'm going to get more pressure. Make sense? This is how the center of pressure looks like depending on, it doesn't matter how you step. This you can look by yourselves. Differences, okay. All right. Stop sharing this. That was chapter 10, so we're done with that. Let's move to chapter 11. Share my screen. All right. We'll have a couple of cool things to talk about here, and we're talking about angular kinetics, right? Kinetics. It said kinetics is explaining how we move. If the line of application of the force does not pass through the axis of rotation of an object, the object will not rotate. I'll say that again, and it will make sense in a little bit. If the line of application of the force does not pass through the axis of rotation of an object, the object will rotate. If the rotation point was right in the middle and the force is going through the middle, then this will not rotate. If it doesn't go through the middle, then it will rotate. Okay? Let's see what's up. Torque, rotational force, okay, equals force times what? The perpendicular distance from the line of action. I'll say that again because it will be important. The perpendicular distance from the line of action of the force to the pivot point. So here, we'll have three scenarios. Scenario A, you see the pivot point. The force is going through the pivot point. Guess what? No rotation. Now the force is all the way to the right. It doesn't go through the, so it goes all the way to the right, right? So the moment arm is huge. The more the moment arm, the more the rotation. The more the moment arm, R, right here. The bigger the moment arm, the more the torque. That's what's happening here. But you see the line of action. Here, what's happening? I'm applying the force on an angle. The perpendicular distance from the line of action of a force to the pivot point. The perpendicular. So the moment arm is this. It's not this. It's this. The black line. So I will have more torque in the B scenario than C scenario and no torque in the A scenario because I'm applying the force to the pivot point. Cool? You can see now generation of torques through scenario A is muscular force, like internal, what I was looking for. External is C, and gravity is in B. Force couple. So let's say you want to jump and rotate, right? You're a gymnast or a skater. Here we have parallel, but opposite, horizontally parallel, but opposite forces. So the left foot is moving. You can see there's a force coming from the front part, and the right leg there's a force coming from the back part. Opposite, parallel though, and the longitudinal axis, you see the point. So that way we have two forces, and we can rotate. That's called force couple, right? It's the force times the distance. The more the distance, the more the force. The more the force, the individual forces, and when we're going to get, the more the force couple we get. Okay, same things are the Newton's laws, but now for rotation. Here, what we have is a longitudinal axis versus transverse axis. All right, let's stay here for a second. Let's see how amazing our bodies are. The measure of a body's inertia is its mass. So the angular mass is what we will be calling the moment of inertia. If we were trying to operationally define it, moment of inertia is the resistance of an object to a change in angular motion. And it depends also on the distribution of that mass around or with respect to an axis. So here we're running. And if we want to enhance angular motion, we have to decrease moment of inertia, right? And if you see here, the lowest moment of inertia is here, right? Which is when the left leg, this is the left leg, you see how it's bent, right? The way we move has an explanation. So when we distribute the mass around the axis of the hip this way, we are lowering the resistance to a change to angular motion right here. And that helps us move faster through the hip and do this movement. This is again the left leg. Okay, so by bending the knee, we're enhancing angular motion. Why? Because we are decreasing moment of inertia. We're decreasing the mass, the distribution of the mass around this axis. All right. I'm going to use that in a little bit when I'm going to talk about cats. C-A-T-S, cats. All right. External torque will produce an angular acceleration that's proportional to and in the direction of the torque and inversely proportional to the moment of inertia of the body. Okay. Now, here I want to talk about one thing. H equals I times omega. So angular momentum is the product of moment of inertia and angular velocity. The more the angular velocity, the more the angular momentum. The more the moment of inertia, the more the angular momentum. Cool. Cool. When gravity, pay attention, when gravity is the only external force acting on an object, the angular momentum remains constant. Why? Because gravity goes through the point of rotation. And what did we say? When a force going through the point of rotation, we have no rotation. So no torque. So here, again, H equals inertia times angular velocity. All right, so the angular momentum remains constant when we only have gravity. If this remains constant, what can we do with the moment of inertia and angular velocity? Let's see what we can do. So we have here a springboard diver, and he or she's on the air. So the moment of inertia, the angular momentum is constant. We can't change that because we only have gravity. So how can we change the angular velocity? We can change the angular velocity because we said that the moment of inertia depends on the distribution of mass with respect to an axis. So when I go to a tack position, what am I doing? I'm decreasing the moment of inertia. By decreasing the moment of inertia, the angular velocity will increase. Why? Again, we said, because this is constant. If this goes down, this will go up. So here, by going into a tack position, I'm decreasing the moment of inertia. By decreasing the moment of inertia, I'm increasing the angular velocity. And I can spin faster, for example. Make sense? Airborne activity. Let's talk about cats. Rotation can be initiated in midair, but it does not violate the law of conservation of angular momentum. Catting. Do you have a cat? You do? Have you ever done this to your cat? I have. Don't hate. It was on a bed, above a bed, so she was fine. So if you grab your cat by the legs up, right, and you let it go, no matter how much space you have between the cat and the bed or whatever, she will rotate and she will land on all fours. You do that with a dog, it's not gonna happen. The dog will just hit the bed. Okay. How does cats do it? Okay, let's explain that through physics. So when, let's say, that happens to the cat, right? So the cat is on the air and her legs are up, her body's down. She is picking her back, like creating a peak, right? Arching her back, that's the word I should have used. And by arching her back, she's creating two different segments of the body, the upper segment and the lower segment. And she has two axes of rotation because she has two segments now. So let's start with the upper body. When she's arching her back, then she's taking her front legs, put it close to her head, and that will decrease the inertia, or the moment of inertia, right? And she will be able to increase the angular velocity and turn. So she's turning her the upper body first. In order to counterbalance that, she's just stretching her back legs all the way and rotating the lower part of your body the other way. So she's rotating the let's say to the right, the upper body, but her lower body, she's stretching her legs and rotating a little bit to the left. After she's done with the upper body, right, she's somewhere between A and B, let's say towards B, then she puts her lower legs, her legs, let's say hands and legs. She moves her legs towards her body. So again, decreasing the moment of inertia. And then she can rotate the lower part of her body. And now she's at C. And then she turns all the way, now we are at D, and she can land in all fours. So we have, let's say hands and legs. Let's put it that way. So she will put or front legs and back legs, whatever you want to say. Let's say front legs. So in the very beginning, arching her back, front legs closer to the body. She rotates the upper part, and then she's stretching her back legs, rotating a little bit to the left, and then she's bending her, pulling her legs closer to her body, her back legs, and then she's decreasing the moment of inertia to the second segment, the lower segment of her body. Then she can rotate the lower segment, and she's at C, and D, and boom. That's how she's doing it. Everything starts with arching her body, creating two segments and two axes of rotation, and taking advantage of this. Angular momentum is the product of inertia and angular velocity. Moment of inertia and angular velocity. And when there's only gravity and it's an external force, it doesn't, the angular momentum has to remain constant. All right. Center of mass is the point about which the mass is evenly distributed, and most importantly, it is the point about which the sum of torques is equal to 0. So C is the point that where all torques, the sum of all torques equals to 0. That does not mean that A equals B. A is 3 kilos, B is 2 kilos. But you can see the distance between them, the moment arm, which makes C the point where the torques, the sum of the torques is 0. And that's the center of mass of this system. Okay, so here, I don't know if I want to confuse you or not. I'll give it a try. Let's say we have 3 different segments of one thing and we're trying to find the center of mass, which you can see is right in the middle. We have this formula up there, and then we'll have these 3 different centers of mass of those 3 segments, right? I have 1.1, 1.2, and 3.3, and I also have the weights at the bottom of each segment. In order to find the x, I'll find the x first and then the y of the center of mass. What I do is I take the formula, m1 is 1 kilo, times x1, which is 1, plus m2, which is 2 kilos, times x2, which is 1, plus m3, which is 3 kilos, times 3, which is x3, equals. So m now will be 1 plus 2 plus 3, so 6 times x. I don't know that x. So when I solve the formula towards x for the center of mass, cmx, the number will be 2. If I do the same thing for y, so 1 times 1 plus 2 times 2 plus 3 times 3 equals 6 times y cm, then I will find that the y for the center of mass is 2.3. So now I have the x and I have the y. The x was 2 and the y is 2.3, and I can find the center of mass this way. That's more for biomechanics though. I hope I didn't confuse you. All right, mechanical advantage. Let me drink some water. 40 minutes, pretty good. All right. Mechanical advantage equals effort arm over resistance arm. So if it is 1, effort arm and resistance arm will be equal. If it is higher than 1, more than 1, the effort arm will be bigger than resistance arm, and the other way around if it is less than 1. Who cares, and what does it mean? Well, when it's above 1, the effort arm is bigger than the resistance arm, which means in a very simplistic way that we can move the same weight with less effort compared to MA being less than 1. So mechanical advantage gives us the advantage of moving something easier. Mechanical disadvantage, it's harder to move the same weight. However, we gain in speed. Let's see what we're talking about. When we talk about levers, we have 3 things: the resistance force, the muscle force or effort force, and the fulcrum. Okay? So here, the first class, it can be 1, less than 1, more than 1. In the human body is usually 1, which means there we'll have 2 equal forces around the fulcrum, which means that they're more for, excuse me, stabilization. Second class is when we have a mechanical advantage. A smaller effort force can balance a larger resistive force. That sounds pretty cool, right? Yes. Bad news is that most of our articulations are not second class levers. Most of them are third class levers, which have a mechanical disadvantage. So a larger effort force can balance a smaller resistive force. However, we gain in range and speed. Okay. First class lever, counterbalancing, equilibrium, right, balance. Second lever, you see now with a little bit, you see the fulcrum is, first class lever, the fulcrum is always in the middle. Done. If it's in the middle, it's first class. Now, if it's not in the middle and the resistance force is closer to the fulcrum, that's a second class lever, which means it's easier, right, to move resistive force. Here, the third class lever is the opposite. So the effort force would be closer to the fulcrum than the resistance force, which means it's harder for us to move or that resistive force, okay? That weight. That's the third class lever. You see now the effort force is closer to the fulcrum or pivot point. All right. Segment torques, if you break it down, okay. Static analysis. When the acceleration is 0, we say we have static equilibrium, right? So here, if there's no movement, there's no acceleration, there would be a static analysis of static equilibrium. When we talk about stability, you see the case A would be something stable because we move something and it returns to the initial position. The B and C that doesn't return to the initial position, the B is unstable, and the third one is neutral equilibrium. The B, you see here, we have an increase in displacement compared to C, where we don't have no return, but we don't have any increase in displacement either. How can we increase stability? We can increase stability if we increase the base of support. If we lower the center mass, and if we increase just the mass from 2 kilos to 20 kilos. Dynamic analysis. All right, work. Torque times angular displacement, right? Can I have negative work? Yes, we've talked about that in 212. And I can have negative work when you can see that there's torque due to the biceps, and there's torque due to the barbell. If the movement of the barbell follows the movement of the torque due to the biceps, that will be positive. Now, if I'm pulling with my biceps, but there is an eccentric kind of movement, right? There, the torque due to the biceps is less than the torque due to the barbell. That's negative work. So I can have negative work. This means that the direction is opposite. Okay? The direction of the force and the direction of the movement. So in scenario B, the direction of the force is going up, the direction of the movement is going down. Power, again, has to do with time. When I'm talking about rotational kinetic energy, we have to, we talked about how we broke it down before. Now that the rotational, we'll have to have rotational kinetic energy as well. So it would look like this, right? Kinetic energy KE plus PE plus RKE. Now you can look at those by yourselves, nothing too fancy. All right, so I'm gonna stop sharing this and I'm gonna first congratulate you for finishing the first textbook, and let's start with the second one. Let's start with motor behavior. Let me share my screen. There it is. Not a lot of slides, so hang in there, just a little bit of an introduction, right? And that introduction has to do with mainly what motor behavior is and what mind-body connection is. All right. Motor behavior definition: the study of human movement created by muscular actions, including why and how movements are planned, produced, executed, learned, and refined. We're going to talk about all this as we go. It includes, be careful, the physiological, aka motor control, and psychological, aka motor learning, aspects of movement. So here, we have motor learning on the left side. That has to do with mind, right, from perception all the way to attention, and motor control, the physiological part, has to do with the body, right? You see musculoskeletal all the way to anthropometrics and movement outcomes. So those two now have to work together. The common ground is the brain. The brain here is the central nervous system, the brain and the spinal cord. So these two communicate, and that's how we have motor behavior. So we have motor learning from one side, motor control from the other side, psychological, physiological, and the common ground is the brain. Okay, that's pretty much the cornerstone of the whole thing we're going to be talking about. All right, so what is a motor skill? It is a voluntary and intentional movement with an outcome purpose. That's, we're really interested in this, in sports especially, okay, and in this class. Movement can be any voluntary or involuntary. So if I digest food, that there's some kind of movement happening in my body, that's not necessarily voluntary. My heart rate right now, not necessarily voluntary, okay? So movement can be voluntary or involuntary. Motor skill is only voluntary movement. So motor skill is a kind of movement, right? Not all movements are motor skills though. Mind-body connection, bidirectional relationship. So the mind affects the body and the body affects the mind. And how it is illustrated in sensation, perception, and psychophysics. All right, let's stop here for a second. Sensation, this physiological detection of physical and physiological signals, like temperature. So if I go out right now, it's 15 degrees. I can feel that. It feels like 15 degrees. Okay? Okay. Let me change a little bit of temperature so I can make a point with my example. So let's say it's 50 degrees. 50 degrees for upstate New York, on average, would be pretty nice temperature. Wouldn't consider that cold. 50 degrees for a Texan, not right now because you see what happened with Texas, but in general, right? That would be considered cold. So they can both sense it. They both sense the 50 degrees temperature, but the New Yorker perceives it as okay. The Texan perceives it as not okay. Psychophysics are examining, investigating, exploring those differences. The difference between sensation and perception. Same thing about water temperature when you're taking a bath. Some people will say, oh, it's too hot. Some people will be like, oh, I love it. Right? So what's going on here and why do we care about perception so much? Let's see some examples before we answer that question. Have you ever seen, do you know what perceived extension is, or RP? Yes. So that's how you perceive something, how you evaluate it, right? How you evaluate how hard you're working when we have you on the treadmill performing a VO2 max test. Okay, So you're going to say something between 6 and 20, and that's how you perceive it. Do you see those visual analog scales? Have you ever gone, let's say, to the airport and you use the bathroom, and then you come out, it has those faces that you click, like if you like whatever was going on in the bathroom or not. That's a visual analog scale, right? That's not for pain, but I'm just telling you. That's a psychophysical tool. That's the RP scale, and 1 to 10 is the modified. All right, so I asked a question like 2 minutes ago. Why do we care about perception so much? Well, we do care about perception so much because usually our actions depend on our perceptions and not on our sensations. So the Texan will get a jacket, the New Yorker won't. Same temperature, same sensation, different perception. Okay? It's a thing called perception action coupling. And that's why we care about perception so much. You see the example, somebody's throwing you the ball, you see it as a threat, you try to avoid it. Somebody's throwing you the ball, you're a baseball player or softball player, you're like, oh, you grab it. Same action, different perception. All right? The more motor skills we have, the better, because in theory, the more tools we'll have in our toolbox, the better we can attack emergencies and non-emergencies. Okay? But as I said before, motor skills are those purposeful skill movements, goal-directed movements, and we really care about those in sports. All right, let's talk a little bit about skill, ability, and talent. Ability is the capacity to do something. If you have the ability to do something, doesn't mean that you have the skill to do it. But if you have the skill, you definitely have the ability. So when let's say there's a baby just got born, he has the ability to jump. If for some reason we put the baby for her whole life on a wheelchair, she will never develop that skill, right? So the baby had the ability, but never developed that skill. A very simplistic example that tells you that when you may have the ability to do something, but if you don't practice, if you don't deliberately try to cultivate a skill, you may not get it. But if you do have the skill, you definitely have the ability. Otherwise, you wouldn't be able to. All right. Talent. What I'm trying to say is that it's not always the ability. Is not something that we're born with it, and the skill is something we have to be taught. It's not necessarily that way. We're going to explain more. I just want to stay here for now. And talent, we're going to explain later on, I think, in chapter 10. So usually we'll talk about genetic abilities when we talk about talent, but it's not that simple either. So we'll just wait, and we're going to talk about it in chapter 10. This is what coordination is. All right, a couple more things, and we're done, promise. Just below 1 hour. Psychomotor skills have characteristics like precision, manual control, cognitive processing, decision-making, and reaction time. Non-psychomotor skills include running and jumping. So non-psychomotor skills do not include all those characteristics of the psychomotor skills. So running doesn't really have to do with precision that much, right? Or decision-making. However, I can take running and I can make you run or jump on some stones, or as part of a game, and you have to be precise where you land, or you have to be precise concerning reaction time. Then I take something that's non-psychomotor and making it psychomotor skill, right? And that's something that we usually do as coaches. We take something that's non-psychomotor and then we create drills. And then all of a sudden it needs cognitive processing, right? We need to think about it. We need to be precise, and we need to react, and we need to make decisions before we move. Right. That was it. I'm going to stop sharing. Here I am. We have LO 10, 11, and 12 due on Sunday midnight. No office hours tomorrow, but on Wednesday from 8 to 12:30. No synchronous meeting this week, but we'll have one next week. Let me know if you need anything. If I don't see you on Wednesday, you'll see me next Monday. In the meantime, lift intentionally, not habitually.